Welcome to the Mechanics of Solid lecture series. In the next series of videos, we will work some examples on simple indeterminate axial systems. Our objectives for this lesson, what I want you to be able to do after completion of the lesson, is to evaluate forces and deflections in simple 1-degree indeterminate systems using considerations of equilibrium and compatibility. Applications may include systems with coaxial or parallel axial members, systems with axial members connected end-to-end in series, and systems with axial members connected to a rotating rigid element. And we will look at an example of all three types. Our first example comes from Mechanics of Materials by Timothy A. Philpott, Wiley, 3rd edition. Problem reads, a composite bar is fabricated by brazing aluminum alloy to a center brass bar as shown in the figure. So basically we have a brass bar sandwiched between two aluminum bars. The elastic modulus for each is given, as well as a bunch of dimensions. W 1.25 inches, A 0.25 inches, the length 40 inches. Problem statement reads, if the total axial force carried by the two aluminum bars must equal the axial force carried by the brass bar, calculate the thickness B required for brass bar 2. Okay, so let's summarize the information that we are given here beyond what is shown on the picture. We are given the elastic modulus for the two materials, E1 equals 10,000 KSI. E2, that's for the brass bar, equals 17,000 KSI. We're given the dimension A is 0.125 inches. We're given the dimension L equals 40 inches. We're given the dimension W equals 1.25 inches. And this is what I want you to do. I want you to, rather than simply on your homework problems, copy the whole problem statement, I want you to summarize what it tells you. Okay? We are also given that the axial force carried by the aluminum bars must equal the axial force carried by the brass bar. I'm going to call axial force in the aluminum bars F1, axial force in the brass bar F2, and I'm going to state that they have to be equal. Notice that we're not given the value of P. Okay? And then what we're asked to find in this problem is the thickness B of the brass bar. Okay? So that's the summary of that problem. Now, we may recognize, hopefully you recognize this, as an example of parallel axial members. These members are acting in parallel. Let's write that down. Parallel axial members. For parallel axial members, they show some commonalities and we'll always be able to approach them the same way. Okay? Now normally for a problem like this I would start by considering equilibrium, drawing a free body diagram. In this case I'm going to do my free body diagram is going to be a cut right through the middle of these sandwich members. Okay? And it's going to look something like this. This is a side view. I have the layers. I have a force P acting on one end. I have the brass member in the middle with a force F2. I have the aluminum members on the end, and they have the same thickness and there's symmetry, so each of those is going to carry a force F1 over 2. Notice I draw my forces in tension. I reason that that is the case, but I will always make that assumption. Let the signs work itself out. Okay? So equilibrium considerations. Let me do sum of the forces in X equal to 0, where I assume forces to be positive acting to the right. And I have P minus F1 minus F2 equals 0 because the total force acting to the left, F1 over 2, F1 over 2 equals F1. Okay? So from equilibrium I would get that P equals F1 plus F2. Now I already know that F1 equals F2, so this tells me that F1 equals F2 equals P over 2. We will see that in order to solve this problem, I really didn't need to know that. However, it's not always this simple, so doing a good consideration of what equilibrium tells you is always a good practice. Okay? The next thing we need to consider is compatibility. And this is where that consideration of the parallel axial members comes in. For parallel axial members that are sandwiched together like this, we can reason that the deflection or the elongation in member 1, the aluminum bar, has to equal the elongation in the brass bar in order for them to say sandwiched together like this. That's the basic consideration of compatibility. So I would write that as delta 1 equals delta 2. This will always, something like this, equality of the deflections will always be your compatibility equation when you have parallel axial members. Okay, now to find the deflections, we use the equation delta equals FL over AE, so we can say F1 L1 over A1 E1 equals F2 L2 over A2 E2. Now this is going to get a little simpler here because we know from equilibrium and from what we're given that F1 equals F2. We also know that the length of the two members are the same. So basically this part of the equation cancels out, and we can simply write it A1 E1 equals A2 E2. Okay? So A1 and A2 are the cross-sectional areas. The cross-sectional area of the aluminum bars, considering the two bars top and bottom, are equal to 2A times W. The cross-sectional area of the brass bar, bar 2, is equal to B times W, where B is the unknown that we're trying to find. So this is what our compatibility equation reduces to. So let me come up here. We can say, solving for B, B is equal to 2A times E1 over E2. Notice the W cancels out of both sides. And substitute in the known values. A is equal to 0.125 inches. E1 is equal to 10,000 KSI. Remember to carry your units through the problem, through the calculations. E2 is equal to 17,000 KSI. And those two units cancel out. The units of the solution will be inches. B is equal to, if you plug that into your calculator, you'll get something right around 0.15 inches, rounding to two significant digits. Okay, so we did get inches. Specify the length or the thickness should be in inches. What's our sanity check here? Sanity check. Well, I note that the thickness of B is on the order of the thickness of A, so that makes sense. It gives me some confidence. I also note that the total thickness of the aluminum bars is greater than the total thickness of the brass bar. However, the aluminum bars are softer than the brass bars, so it makes sense that in order for them to keep the same deflection, the aluminum bars, if they're softer, would have to be a little thicker in order for them to carry the same force. So my sanity check, my reason check is that the thickness B should be less than 2A, so I think the answer looks good.